Hey everybody, this is Mr. Beckstrom, and today I want to talk about section 2.3. I'm going to do a quick overview, and this is techniques for computing limits. So the first one is probably pretty intuitive here, but let's go ahead and talk about it real quick. It says Theorem 2.2, this is on page 71. It says let a and b and m be real numbers for linear functions such that the f of x is equal to mx plus b. The limit as x approaches a of f of x is equal to f of a, which is equal to ma plus b. So what does this mean? Well, it means if we have some kind of linear function, remember a linear function is going to be a straight line here. The nice thing about linear functions is that they are continuous, and that means that the limit from the left and the limit from the right for every point A on this linear function is going to be equal to the function defined at that value, and the one-sided limits there as well. So if I took a point A here and I was coming from both the left and the right, notice that on all linear functions we're going to be approaching some y value. We call that f of a, and f of a should also be defined at that point. Why? Because linear functions are defined, they have a domain of all real numbers, so that means that from negative infinity to positive infinity, there's no point where they're not defined, and then they're also continuous, which means that you're not going to have a hole in the line with some other point being where the function is defined at. So here's the first one. So now let's kind of move on to the second one. If you want to take a look at a couple of examples, you can look at example 1 on page 71. But I want to talk a little bit more about the limit laws. All right, this is on page 72. It's theorem 2.3. It says assume that the limit as x approaches some value a of our function f of x and the limit as x approaches a of some function g of x exist. That means that they are defined for some value of a. And the following properties hold where c is a real number and n is greater than 0 and an integer. So the first one here says the sum of the limits is equal to the limit of the sums. So here's the limit of the sums, and then we can actually separate that into individual sums there. And we can do the same thing for the difference. So if we have the limit of the difference, that's equal to the difference of the individual limits there. We have a constant multiple. That means that if we're taking the limit of some function times some real number c, that we can actually take that c and pull it outside of the limit and evaluate the limit of just that function and then multiply it by that value afterwards. The same kind of thing with the product here. So if you take the limit of the product of two functions, we can separate that into the product of the individual limits of each of those functions. The same thing for the quotient, provided that the limit as x approaches a of g of x, that's the bottom limit there, is not equal to 0, because when we try to divide by 0, bad things do happen. This one here says that if we're taking the limit of a function to a power, that we can actually take the limit of just that function and then raise it to the power afterwards. And then the same kind of idea holds for the roots. So instead of taking it to just like power n, it's power of 1 over n. And this is providing that f of x is greater than 0 for x near a if n is even. If n is even. Why does n have to be even? Because then we're only looking at the positive roots. All right, so let's go ahead and look at an example here. All right, so this says assume that the limit as x approaches 1 of our function f of x is equal to 8, that the limit as x approaches 1 of g of x is equal to 3, and that the limit as x approaches 1 of h of x is equal to 2. It says compute the following limits and state the limit laws used to justify your computations. All right, so we have the limit as x approaches 1 over f of x divided by g of x minus h of x. Now, I can't just replace the f of x, the g of x, and the h of x with values because I don't know what they actually are according to what's given. This is not the value defined at a certain x value. This is the limit, and those two things are different. So we have to use some of these laws in order to break this up, so we can go ahead and use these here. So myself a little bit more room. So the first one I want to use is, this is a quotient here. So what I can do is I can say, due to the quotient law here, the limit of this function over this function, and I'm going to treat f of x as one function and g of x minus h of x as another function. And then I'm going to write that as the limit x approaches a of the top function here is over the limit as x approaches a of the bottom function. So right now what I'm going to do is I'm just going to use the quotient rule to say the top is going to be the limit as x approaches 1 of f of x, and the bottom is going to be the limit as x approaches 1 of g of x minus h of x, like this. All right, so now I know what this one here is. That one is just going to be equal to 8, but this one here, I'm going to have to break that up again, and this time I'm going to use, let me do that. This time I'm going to use the difference one. So if I have a difference of two functions here, I can break it up into the individual limits, difference of the individual limits. All right, so I'm back over here. So this is going to be equal to the top is just this whole limit as x approaches 1 of f of x is just equal to 8. And the bottom now is going to be, we can break that up into the difference of individual limits. So x approaches 1 of g of x minus the limit as x approaches 1 of h of x. All right, so now it looks like this. Now I know what this limit is because it defines it there. I know what this limit is. It defines it there. So finally I'm going to have 8 over 3 minus 2, which is equal to 8 over 1, which is equal to 8. And that would be my answer for this problem right here. All right, theorem 2.4 says the limits of polynomials and rational functions. Assume that p and q are polynomials and a is a constant. So let's talk about what a polynomial is. It's something that looks like this. This would be a third degree polynomial. So 3x cubed plus 2x squared minus 5. This would be a polynomial here. So this is where all of the coefficients are real numbers. And then we have x's to all non-negative integers. So it could be x to the 0, which is really what 5 is, right? 5 is really just the same thing as 5x to the 0 because x to the 0 is equal to 1. But it has to be a non-negative integer. So it could be 2, it could be 3, it could be 6, it could be 8. These are what I can have for this to be a polynomial. We've done a lot with quadratics. Quadratics is when the highest exponent is a 2, and we have a polynomial degree 2. And the nice thing about polynomials is that when we graph them, regardless of how large the largest exponent is, we always get these nice smooth curves, right? And the number of hills and valleys is going to be dependent upon the highest degree of our polynomial. Like a quadratic is just going to have either one bottom or one top there. It's a parabola. However, the nice thing about these is that since they're continuous functions, that means that for any point A on here, if we look at the value of f of A, that's the y value, the limit from the left is going to be equal to the limit of the right, which is also going to be equal to the function defined at that value. So that means that if we're looking at the limit as x approaches a of some polynomial, that's just going to equal to whatever the value is when we plug in that a there. And for rational functions, it's the same kind of thing. If we have a polynomial divided by a polynomial, that's just going to be equal to the top polynomial evaluated at a divided by the bottom polynomial evaluated at a, provided that the bottom is not equal to 0. Nice little intuitive theorem here, but we're going to be working a lot with polynomials in calculus because they have a lot of these great properties, mainly being continuous and differentiable for all real values of x. All right, let's go on to the next one. All right, so if we look at theorem 2.3 continued, and this is on page 74, it says that the laws 1 through 6, these are the ones up here, will hold for one-sided limits, and we went over one-sided limits in detail in section 2.2, except for the root limit law here. That's number 7. They made a slight modification. Notice that if you're talking about the limit from both sides, our f of x has to be strictly greater than 0. But if we're just looking at one-handed or one-sided limits, I always say hand, I don't know why, one-sided limits, then it's greater than or equal to 0. So it allows the function to actually be 0. It still has the requirements that n has to be even. And then since these are one-sided limits, if we're coming from the right, x has to be greater than a, and if we're coming from the left, x has to be smaller than a. So let's go ahead and take a look at an example here. All right, so here we have a limit. It says the limit as x approaches -1 of 2x minus 1 quantity squared minus 9 over x plus 1, and we want to find out what the limit of this is. Now the first thing that we really want to do here is, since we have a polynomial over a polynomial, is we want to just go ahead and plug in the -1 in the top and the bottom. And if we do that, let's see what we get. So on the top, we're going to get -1 times 2, which is -2, minus 1, which is -3. So that's going to be -3 squared minus 9 over, and on the bottom we're going to have -1 plus 1. And when we do that, you're going to get 9 minus 9 over -1 plus 1, which is 0 over 0. Now this is hugely important when we talk about limits. This is called the indeterminate form, and that's where we have a 0 over 0. There's some other indeterminate forms as well, but this is the one that we're going to be talking about for right now. And when we see that form, that means that we cannot determine what the limit is at this point. Now, very often, especially in this class, we design problems so they have what's called removable holes, which means that if we do a little bit of multiplying and factoring, we might be able to see that this value here at -1 is just a hole there. And remember that even though it might not be defined, this function might not be defined at -1 because that gives us a 0 in the denominator. It still might have a limit because we don't have to have the the actual x value there in order to have the limit. So as long as from the left and the right it's approaching some value there, then we can actually still have a limit. So the first thing I really want to do with this problem is I'm going to put this into my calculator just to kind of see what it looks like it's doing at -1. Alright, so let's go ahead. We're going to go to y1. I'm going to put the entire top in parentheses. That means I need to start with 2 open parentheses. So 2x minus 1 squared minus 9, and close parentheses, and divided by open parentheses, put the entire bottom in parentheses, x plus 1. And I want to see what it's doing when x is equal to -1. So let's go ahead and zoom. We'll do a standard zoom at first. And if I see that here at x equals -1, our y value, and if I hit trace here, oops, trace, there we go. So I'm going to get this as close to, x equals -1. Let's see if I can get it over there. And x equals -1, my y value is really close to -12 there. Let's go ahead and I'm going to change this window so it goes down a little bit so I can see that a little bit better. And all I'm going to do here is go to Window and go to my y minimum and change that to -15. So it goes down a little bit farther, and go back to Graph. And as we can see now, if I hit the trace function and I go to x equals -1, I can kind of more clearly see that it's going to be pretty close to -12. And so even though there's a hole there, because at -1 we have a 0 in the denominator, it's not going to be a vertical asymptote. So that means that this is what's called a removable hole. So if we can factor out this term, x plus 1, then we can actually see what the limit is. I know it's kind of complicated, but as we do a few of these, they'll start to make more sense. So what I'm going to do is the limit as x approaches -1. I'm just going to start multiplying this, play around with it. Like I said, see if I can get a common factor of x plus 1 on the top and the bottom. If I can, I'm going to cancel those out and then see what I have left. So this is, I'm going to multiply this top part out. So 2x minus 1 is going to be 4x squared minus 4x. And then I have a plus 1, but I also have a minus 9. So that's going to be minus 8 all over x plus 1. X plus 1. And I can factor a 4 out of the top. So this is equal to the limit as x approaches -1 of 4. And that's going to give me x squared minus x minus 2 all over x plus 1. And finally, I want to factor that out right there. Let me give myself a little bit more room. So this is going to be the limit as x approaches -1 of 4. And we can factor this to, looks like x minus 2, x plus 1, x minus 2 times x plus 1 all over x plus 1. And sure enough, those two factors cancel out. So this equation here is equivalent to this equation there, except at the singular point of x equals -1, because in this equation here we're going to have a hole at x equals -1, but in this equation here we don't. But remember, limits don't care about holes. They just care about what y value we're approaching from both sides. So now if I actually, remember this is a polynomial too, so now if I put the -1 in there, this is going to be the limit as x approaches -1, and now of our function 4x minus 8, which is just going to be equal to, since this is a polynomial, the function at -1 and this is going to be negative 4 minus 8, which is equal to negative 12. And that's pretty close to what we saw on the calculator there. So if we kind of go back and forth between there and there, we see, sure enough, that looks right. And that is our answer. All right. All right, finally, I want to talk about theorem 2.5, and this is the squeeze theorem. It's a good name. It fits this well, and it says, assume that the functions f, g, and h satisfy this property, that g of x is really between f of x and h of x. So the function here is greater or equal to f of x and less than or equal to h of x. So what does that mean? Let's talk about that real quick here. I'm just going to do a really coarse graph here, but let's say we have some function g of x that just goes g of x, right? G of x. So this function here that goes on is g of x. In order for this to be true, that means for every value x, g of x is going to be greater than or equal to f of x. So there's nowhere where this thing is allowed to cross over the top of g of x. It can be equal to g of x at any x value, but it can't be on top of it. So here is my f of x. Because remember, f of x is less than or equal to g of x for every value of x. And my h of x has to be greater than. So my h of x up here has to be greater than or equal to g of x for every value of x. So we have to be able to first show that g of x is between these two things for all values of x near a except possibly at a. And if the limit as x approaches a of f of x is equal to the limit as x approaches a of h of x, which is equal to some value L, then the limit as x approaches a of g of x is equal to that L. So that means that I probably should have did this a little bit differently. Let me go ahead and, well, I mean, this is correct, but let's say this function does satisfy that, and the only point that it touches is right there, right? So here is my f of x, and my h of x is up here, and it only touches there, but it doesn't cross over. Oops. So it just touches right there. It doesn't cross over, so here is my h of x. So this satisfies this definition here. And here it says that the limit of the top function is equal to the limit of the bottom function. So if we look at x approaches a, like right here, and we see that the limit of the bottom function is approaching some f of a, which is equal to our limit there, and the top function is doing the same thing. It's approaching that same L. Then the limit as x approaches a of g of x has to be that same L, because it can't be above h of x and it can't be below f of x. And that is called the squeeze theorem. So let's take a look at an actual example and see how that works. Alright, so let's take a look at this limit. This is the limit as x approaches 0 from the left. So we're only looking for negative values of x, of the function x cubed times the cosine of 2 over x. Now, if we try to put a 0 in there, notice that we're going to get a 0 times the cosine of 2 over 0. And this is going to be undefined there, so we really can't take a look at the limit of this in the normal way that we have been. So what we're going to do is we're going to attempt to use the squeeze theorem. So very common with these types of problems, when we see a trig function in there, we can start by saying we know that the cosine of any angle, now remember, 2 x cannot be equal to 0 because it's approaching 0 from the left-hand side, so it's never actually getting to 0. So we can write this. But we know that the cosine or the sine of any angle has to be between what two values? Well, according to our unit circle, it can never be greater than positive 1. It can never be less than negative 1, right? Because if we take the cosine of any angle or the sine of any angle, once again, the minimum value is going to be negative 1, and the maximum value is going to be positive 1. So that's what I'm going to do here. I'm going to say we know that this has to be less than or equal to positive 1, and it has to be greater than or equal to negative 1, right? Because we can kind of squeeze any cosine or sine function into these two values here. Now, the next thing I want to do is, remember, I'm trying to get this function back, so I'm going to multiply everything by x cubed. So this will give me negative x cubed is less than or equal to, that should be better, 3, the x cubed times the cosine of 2 over x, which is less than or equal to positive x cubed, right? So we have this function here because we started with, we know that the cosine of any angle has to be between positive 1 and negative 1, and then we just multiplied everything through by x cubed. Now, so we have this criteria met up here, right, where our first function is negative x cubed, our second function g of x, the middle function is x cubed cosine 2 over x, and then the last function is h of x, which is going to be x cubed. And now all we need to do is look at the limit of the first function as x approaches a, which our a is 0, and the limit as x approaches our last function. And if those happen to be equal, then we know that that function that is squeezed in the middle, that is kind of nested right in the middle of those two functions, has to be that same one. So let's look at the limit. We'll start with the f of x function, the first one. So the limit as x approaches 0 from the left of negative x cubed. Well, we can pretty easily see, since this is a polynomial there, we can just plug that 0 in, even though it's a one-sided function, because we just looked at the laws for one-sided functions, and this is just going to be equal to 0. I'm going to do the same thing with the h of x. So x approaches 0 from the left of positive x cubed. Once again, we have a polynomial there, so I can just plug that 0 in, so that's just equal to 0. So now we know that the limit as x approaches 0 from the left of this is 0, of this is 0, and since those two are equal, that means that this thing here has to be 0 as well. So that means that due to the squeeze theorem, that this last function here of x cubed, my cubes are horrible today, times the cosine of 2 over x has to also equal 0. Alright, and the last thing I want to do, I know this is kind of a long video here, is I want to put all of these functions into my calculator and just see what it looks like. So let's go ahead and let's change this window back to -10, or it doesn't, we don't have to do that, we can just do a standard zoom. Alright, so I'm going to do my first function is negative x cubed. I'm going to do my second function as this one here, so that is x cubed times the cosine of 2 over x, cosine of 2 over x. And whenever I am graphing trig functions, it's usually almost always good to make sure that we are in radians, which I am. And then the last one is just going to be positive x cubed. Positive, oops, clear, x cubed. All right, and remember, I'm trying to look as x approaches 0 from the left. So let's go ahead and do a zoom standard. And as you can see, I don't know if you can see, but we can hit the trace function. And this first function here is my negative x cubed. So it kind of goes like this and like this. My red function there is probably going to be my, my one that's in the middle there, right? And then finally, my black function will be the negative x cubed. Oops, the positive x cubed, excuse me. And you can see that right when we get to 0 here, let me do a zoom box. Oops, get a little bit closer there so we can maybe see a little bit better. Enter. All right. And sure enough, the limit as they approach 0 from the left-hand side is all the same thing. We can actually see it's kind of the same from the right side as well. All right, guys, if you have any questions, please let me know, and I hope you have a great rest of your week. Thanks.